recording. Okay, so here we have this setup. Let me make sure everything is good. As far as I said, I made a recording twice, but I was just using the app. I wasn't using the computer, and it didn't work out. It just converted the video into a file, which is not useful to you because I did all this work and that wasn't captured. So I have to make sure that everything is okay. The recording is going on. I am sharing my screen and you can hear me. Okay? We will start. So I went over chapter 4. So you see scribblings that I made yesterday. Just ignore it. I'll erase it and start from scratch. Chapter 4 outline, we're starting with energy. So at some point, we're going to be figuring out the energy that is present in different compounds or substances such as food or gasoline. And as far as the assignments are concerned, I just stuck with food. I figured we can all relate to that, right? So before we start figuring out how much energy is in food, we'll start by defining what energy is. Energy is usually related to doing work. When you're tired and you've done a lot or you're just tired, you usually say, I feel that I have low energy, I can't do any work. So even in the world outside of chemistry, we relate energy to work. We have two main types of energy that we talk about, and we want to be able to distinguish one from the other. Potential energy is the stored energy. So this is the energy that's contained in bonds. So right here, contained in bonds. Okay, and then kinetic energy is the energy in motion, and this energy has to do with something in motion. So it's the energy that allows something to move, and while something is moving, it is using that kinetic energy. So we'll talk about kinetic energy, and this has to do with motion. As we're dealing with energy, we have to look at energy holistically. And we look at it by examining the law of conservation of energy. And this states that the total energy in the system does not change. Energy cannot be created nor destroyed. Okay, so as we look at that, please notice here, once again, as I said, I had already worked on all of these yesterday and I have to just do over. Anyway, depending on the area of science, sometimes energy is communicated in the units of calories and sometimes it's the units of joules. So I tend to have certain favorite snacks like a Snicker bar, and I used to remember how many calories it has. I think I've forgotten. It's been a long time. But this calorie they're defining here is different from the food calorie. This calorie is a unit of energy. It's the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. So this is a technical definition of what a calorie is. And a joule or 1 joule is another unit of energy. So we want to see how the calorie and the joule are related to each other. They are related to each other via this equality right here. So when we talk about 1 calorie here with a small c, we're talking about 4.184 joules of energy. So for the most part in the lab, we deal with joules, units for energy. So this is the lab. Sometimes we talk about energy in terms of calories, but joules is a more common one in the lab. When it comes to food, we deal with kilocalories and not calories. But the kilocalories is actually rewritten as calorie with a big C. Okay, so I don't know exactly where this originates, but at some point, the food was labeled as calories with a big C, and those of us in science understand that the calories with a big C actually replaces the kilocalorie that relates to the calorie unit we deal with in labs. So remember that the calorie is related to the joules. We're told both joules and calories can be reported in larger units as kilojoules and kilocalories. So you want to know the equality for kilocalories and kilojoules. It's the same as the one above. Remember, oh, hold on a second. Remember that kilo stands for 1,000. Okay. So as we talked about this right here, once again, I need to erase all this because I worked on this yesterday. Okay, we're now looking at the amount of energy that's stored in food, and we're going to be focusing on figuring out the amount of energy. Now, imagine you got hired to do a job where you were figuring out the amount of calories in food at a restaurant, and this is your job, and they hired you. So you want to know how to do this. We usually figure out the amount of calories in the macronutrients, right? So we're dealing with proteins, carbohydrates, and fats. We're told the amount of stored energy in food is measured using the nutritional calories with a big C, uppercase C, where 1 calorie stands for 1,000 of the regular calories. Can you imagine that? If you're eating a candy bar that has 250 big CAL, you're technically eating a candy bar that has 250,000 of the regular calories. Oh, with a small c. I have a bad habit of writing the small with the big and vice versa. But imagine that 250,000 calories. But I guess if people saw all those calories, they will actually think twice before they eat. So then, if that's the case, why don't the manufacturers post that instead of this? I'm just asking. Okay. Okay. Upon metabolism, proteins, carbohydrates, and fat each release a predictable amount of energy, the caloric value of the substance. So if you're a calorie counter person, I am one of those people. I count my calories. I look at the food with my eyes and I'm like, yeah, this is the right number of calories. That's not how you do it. I'm just kidding around. Okay, so we're told here that for every gram of protein, we have about 4 4 calories. So 4 food calories. For every gram of carbohydrate, we have 4 food calories. For every gram of fat, we have 9 food calories. You can see that fat is actually packed with so much energy. And that's what they're saying, that when you're eating, you need to watch the amount of fat you eat, because any unused energy, guess what happens? If 1 gram of fat can be converted to 9 calories with a big C, then if you have any excess energy in your body that you didn't use, guess what happens to it? It gets converted to fat, right? So this is kind of like an interchangeable relationship. The fat can become the energy, and then the unused energy can become the fat. Okay, so essentially, when you're in the gym burning off calories, you're just doing this process here and converting the grams of whatever it is, carbs, fat, proteins, into calories. And that's why, okay, so now I'm just kind of going off script, right? But when you see people who work out too much, they look skinny because they're not only burning fat and calories, they now begin to burn their muscle, right? And so people who work out a lot have to take in more protein to make sure they're not going ahead and burning off protein. Guys, I can go on and on. This area of chemistry is very interesting to me. Anyway, so after we've seen that, I won't erase everything. I'll just go over what I've written right here. So essentially, 1 gram of protein is equal to 4 calories, food calories, right? So you can write it like this as an equivalent, or you can write it as a ratio. As a ratio, it looks like this. So the ratio is useful for converting, okay? Like that. You can write it this way with a big C, food calories, or 4,000 regular calories. For the most part, we'll be dealing with food calories. When they ask you about food, they will want food calories, okay? With the carbohydrates, same thing. 4 calories, food calories of carbohydrates are stored in 1 gram, okay? You can once again use it this way as a fraction, as a ratio when you're trying to convert. Finally, fats. When I talk about fats, I'm like, yes, okay. With fats, I'm sorry. Just when I sit down to record, I start getting all these emails. So, okay. So with fats, every 1 gram of fat gives you almost, not almost, a little bit more than twice, right? But fats are so tasty, though. Y'all know with meat, when it's marble with fat, it's so tasty. But we're told just 1 gram of fat holds all these calories. It's a lot of calories. So the more fats you eat, the more you must burn to actually burn off that fat. The more you must work out, right? So 1 gram of fat holds 9 calories. Okay. So essentially, what is the takeaway lesson from this? We get more energy by eating fats. As I think about fats right now, I'm like, I know it's not good for you, but we get more energy. But it's more energy that you're supposed to use to do something. Convert it to kinetic energy, not potential, right? You don't want to just be at the potential stage, just storing, storing, storing. You want to burn it off. Okay, so I worked on this one yesterday too. And yesterday I was like, sounds good. If a baked potato contains 3 grams of protein, so I'm thinking baked potato. Since I've read this question yesterday, I realized it wasn't a baked potato that was loaded. It was just a regular baked potato before you put anything in it. So in this baked potato, we have 3 grams of protein, a trace of fat, 23 grams of carbohydrates, and they wanted you to figure out the number of calories, food calories with a big C. So when you're working on this, make sure you're keeping track of which C they're giving you. Oh, I just realized here, I can go ahead and rewrite this. So I have my conversion factors here on the right. I'm not going to erase that. Big CA. It has a trace amount of fat, so there's no need for the fat conversion. But if we wanted to write it here, we could write 1 gram of fat equal 9 food calories, right? Big CAL. Okay, so over here, what do I have? Oh, let me write down what they gave me. So in one potato, right? That's my potato. I have 3 grams of protein. I'm surprised there's that much protein. And 23 grams of carbohydrate. I'm not surprised about the carbohydrate part. And then the fat in the potato is not significant enough. Okay. So our operation, our math will be done by taking the given, multiplying it by the conversion factor to get our answer. Okay, so we have two numbers right here. These are our given. We were given a potato, not a real potato, a theoretical potato. I don't think it's a Stacy, it's a real one. Okay, so you want to start with your given. So I wrote down, I started off with my protein right here. It's important as we're working on this to make sure the unit of the given, so grams of protein, when you use your conversion factor, the grams of protein on the top left has to diagonally match the grams of protein on the bottom right. You see that? So they can cancel out. So you're going to convert this right here into a fraction. Put the gram of protein on the bottom part right here. Put the calories on top. And when you work this out, 3 times 2, we end up with 12 calories. So from the protein in the potato, we get 12 calories of energy. Okay, we all know, I mean, if you work out, you know that you get more energy from carbs than you do proteins, right? Well, I shouldn't say you get more energy. Uh, Carbs are a more readily available source of energy than protein. So we get the same amount of energy. It's just that the energy in carbohydrate is more readily available. And I don't think we're going through the Krebs cycle just yet. No, not yet. We're going to be doing that way later, where we see how the body processes this energy, and we can see that carbs have more readily available source of energy. So if you're somewhat feeling low in energy and you want a quick shot of carbs, or sorry, a quick shot of energy, you want to eat something that's full of carbs, right? Slice of bread, whatever. If you want the energy to last for a longer time, then you want to get protein. Okay. So now we're working on our carbs. Once again, make sure grams of carbohydrates on the top. Use your conversion here. Put the grams of carb on the bottom. That will go right here. On top, we have 4 calories. When you multiply this out, you get 92 calories. Okay. And then when you add all the calories, now you get 104 calories. So imagine this is you working at a company, right, that grows potatoes. And you can say, okay, you're working on the calorie content that gets printed on the label. And this is your job. Not bad, right? And they pay you. So here we have this right here. They did the math, got a similar answer. Now we are moving on and talking about the 3 states of matter. With the three states of matter, we're talking about this because when we get into the organic part, we're going to be looking at matter and how the intermolecular force affects the state of matter. So, oh, come on. It's like I erase it, and then as soon as I lift up the pen, everything just comes back. Okay, we're looking at 3 states of matter. In chemistry, we deal with the gas state, the liquid state, and the solid state. So we're told here whether a substance exists as a gas, a liquid, or solid depends on certain factors. What are these factors? It depends on the balance between kinetic energy of its particles and the strength of interaction between the particles. Okay, so I'm going to take a little detour here and tell you, I'm paraphrasing what they said. What they're essentially saying is the three different states of matter that we know pretty much exist, right? But these exist because you have two competing forces. So we're told for atoms, there are two competing forces that will then determine the state that we see in the chemical. We have kinetic energy, and this is the energy of the individual molecule. It can be a particle, it can be a compound, and this energy allows the molecule, the particle, the formula, whatever it is, the chemical, to move freely. Okay, so this is like the individual energy. And then you have another energy that's called the intermolecular force. I call this also the group force. So the force that holds the different molecules together. You have individual energy, the energy within the molecule, allowing it to move freely. And then you have the interaction between the particles, the formulas, the chemicals. These are atoms and molecules that keep them together. Okay. Remember that this interaction is always an attractive force. Okay. So there's that competition. The bottom line is this. If the kinetic energy is greater than the intermolecular force of attraction, if this is the case, you have a fast moving molecule. Okay. So let's look at the gas. I'm going to look at the gas. We'll look at gases first, move into liquids, and then we'll go to solids. So with gases, I've drawn a picture here that represents the gas molecules. These molecules are widely spaced apart. Gas molecules move fast, and they move fast because the kinetic energy is high. The intermolecular force of attraction is low. Why is it low? It is very low because the gas molecules do not attract each other very much. Some books say they don't even have an attraction for each other. It's like one gas molecule sees another one and it's like zero attraction. So for that reason, the lack of attraction between the gas molecules allowed the gas molecules to have freedom. So these gas molecules, I say here, gas molecules have the greatest freedom. Okay. Well, with everything in life, there is a cost, right? Because they have a lot of freedom, because they don't hold each other back by that group intermolecular force, they sacrifice certain things. So, what do gases sacrifice? Gases sacrifice the volume and the shape. Okay? Gases don't have their own volume, gases don't have their shape. Gases have to rely on a container that they're placed in to define their volume and to define the shape. Gases will just spread out indefinitely if there's no container to contain them. Okay? There is a price for that freedom they have. And then we have, I'll go the other extreme. We have solids. Solids, the molecules are organized and they're packed very close together. Okay? They're the opposite of gases. Kinetic energy is very low. Oh, hold on a second. Hold on. Sorry. Once again, it's just people at work emailing me, calling me. Sorry. Okay, where was I? Yeah, kinetic energy is very low. Intermolecular force is very high, right? The intermolecular forces hold these particles together. It's kind of like a glue that holds them together, okay? And then we can move on to liquids. Let's look at liquids and see what's going on with liquids. With liquid, oh my goodness. I'm sorry, guys. Sorry. Let me just tell them real quick. Hold on. Okay, sorry. I have to my coworkers. I'm actually doing a recording. Okay, so where was I? Yeah, the kinetic energy is very low. The intermolecular force is the highest, and then you have the liquid that's somewhere in between. Kinetic energy is not very high. It's kind of intermediate, and so is the intermolecular force. Okay. So what I talked about essentially is discussed right here. Sorry, it's just my work environment isn't exactly ideal. Okay. So as we look at this right here, they talk about the shape and the volume. Gases will expand to fill the whole container, while solids have their own shape and their own volume. Okay. And then fixed liquids have their fixed volume and they take the shape on the container. So liquids, they have their own volume, but they rely on the container for their shape. So it's kind of like halfway between the two. Uh, Gases are usually spread out. They're disorganized. They're very far apart. Solid particles are arranged very closely. They're very organized. Liquids are randomly arranged. Okay. Density of gases is very low because it's spread out. Density of solids is very high. They're packed together. Of course, the liquid is intermediate, right? It's in between. The particle movement very fast in gases. They're moving very fast. They're very high energy. Solids are very slow. They just vibrate in place. And then the liquids kind of slide past each other, just slide to the left, to the right, and then just kind of sliding past each other. That is why we can pour liquids. Interaction between particles, you see how it says none, right? And then with solids, interaction between particles, very strong. Okay, so here we go into the intermolecular forces. So what I'm going to do here is, I know I haven't been talking that much, but I'm going to stop the video here. I'll post this and I'll come back and start from here because the amount of emails I'm getting is a lot. And so I need to address whatever they're emailing me about, and I'll come back and record the continuation of this. So let me go ahead and stop. Sadly, with what I have on Collaborate, I can't pause and come back. I have to stop the video and record the continuation. So I'm going to start here. I'll write for myself, start here so I can come back. Okay. Okay, hold on just a moment. Let me stop the recording.